Surely this graph is a parabola opened upwards. We recall that this graph corresponds to a quadratic expression ax square plus bx plus c with a greater than 0. What can we conclude by seeing the graph? This particular parabola meets x-axis at exactly one point only, say alpha 0. It does mean that if you put ax square plus bx plus c is equal to 0, practically you are getting only one value, that is alpha. And that case is explained in what way we explain generally? That quadratic equation has two equal roots, alpha and alpha, and that can be observed with the case d is equal to 0. So this diagram corresponds to two particular cases. One case is a is greater than 0, other case is discriminant d is equal to 0, that is it has two equal roots, the two roots are alpha and alpha. One more very important observation here to make is the entire graph is above x-axis. Not even a single inch of that falls below x-axis. Every part of the graph lies above x-axis. Above x-axis means positive region in view of y coordinate. That is, the expression is always positive. Positive or non-negative? It is. How can you say ax square plus bx plus c is greater than or equal to 0? Why can't you say that it is definitely greater than 0? There is a particular point here alpha at which the expression becomes 0. Therefore, except that alpha, everywhere that expression is positive. Ax square plus bx plus c greater than or equal to 0 for all x belongs to R except alpha. So, if x is equal to alpha, then ax square plus bx plus c is definitely greater than 0. That is, ax square plus bx plus c is greater than 0 for all x not equal to alpha. Let us make similar types of comments in view of that adjacent diagram also. Let us turn our head towards this diagram. How does this graph appear? This is again a parabola, of course opened downwards. What can you say? A is less than 0. In view of the expression ax square plus bx plus c, a is less than 0. As before in this case, here also the curve cuts x-axis, rather meets x-axis at exactly one point. Let it be say alpha as before. Let us name the same alpha. So here also the graph meets x-axis at one point only. Therefore, if you put x square plus bx plus c is equal to 0, practically you are going to get only one numeral, and we express that idea in that way, in this way. What is this way? That equation ax square plus bx plus c is equal to 0 has two equal roots alpha and alpha. And to observe this, rather to confirm that, we should have d is equal to 0. By looking at d is equal to 0 itself, we are able to conclude that it has two equal values. Well done. In this particular graph, the important thing that one has to observe is the entire graph lies below x-axis. The entire expression lies below x-axis. Below x-axis means the negative region corresponding to y coordinates. What is y here? Expression. So we declare that this expression ax square plus bx plus c is always negative or can never be positive. Okay, why should we write less than or equal to 0? Why don't we write less than 0 exactly? There is a point alpha at which the expression becomes 0. Therefore, ax square plus bx plus c is greater than or equal to 0, less than or equal to 0 for all x belongs to R. Here also in the previous case, we need not write here like this. For all x belongs to R. And if you want to say ax square plus bx plus c is exactly less than 0, then what happens? Ax square plus bx plus c is less than 0 for all x not equal to alpha. For all x not equal to alpha. This is a beautiful case. Basing on this simple concept, so many questions are asked in so many competitive examinations, especially JEE, and the question and the data looks clumsy unless you are cautious of observing it. Let us now observe one such question regarding this concept. One more case is there to discuss with, that is when the equation does not possess any real roots. What will be the case? Observe the diagram. Look at the graph. Is it opened upwards or downwards? Opened upwards. Therefore, what should you observe? A is greater than 0. Does it make any friendship with x-axis? That is, does it cut anywhere on x-axis? No, not at all. Not even a single point. This does not meet x-axis at all. That is, even if you put ax square plus bx plus c is equal to 0, you are not able to have any real value of x. That is, that equation ax square plus bx plus c is equal to 0 has no real roots at all. And to establish this, we notice that d is less than 0. Come on. At this juncture, we observe that entire graph lies above x-axis, exactly above x-axis. Just like in the previous case, we are not able to get even a single point on x-axis intersected with the graph. No such point is there. So at this moment, for all real values of x, the graph always lies above x-axis. That is, ax square plus bx plus c is always greater than 0. For all x belongs to R, no hesitation at all. For any real value of x, this expression always positive is always positive. How can we conclude that? The graph lies entirely above x-axis. That is why we say that the expression is always positive. Well, just like this, let us have a look towards this diagram. It is again a parabola. Of course, it is opened downwards. That is, a is less than 0. Moreover, just like in the previous case, there also the parabola does not meet x-axis at all. No points can be seen on x-axis relative to the graph. So, ax square plus bx plus c is equal to 0 cannot possess real roots at all. Hence, here also the discriminant d is less than 0. Come on, observe the graph, observe the position of the graph. It lies entirely below x-axis. It is always supposed to be negative because the region below x-axis is said to be the negative region related to y coordinates. Yes, below x-axis means either fourth quadrant or third quadrant. In both these quadrants, y is negative. What is y here? The expression. Hence, the expression y, that is ax square plus bx plus c, is always negative. Ax square plus bx plus c is always negative. Let us have a comparative study between these two graphs. In both these graphs, the common feature is the curve does not meet x-axis at all. That is, the equation ax square plus bx plus c is equal to 0 do not possess real roots at all. Well, the different aspects are, here a is positive, hence the expression is always positive. There a is negative, hence the expression is always negative. Yes. So, this is a very good concept which helps us a lot in so many typical questions. Let us get and answer one such typical question now. If f of x is equal to ax square plus bx plus c, and a greater than b square by 4c, a plus b plus c greater than 0, then first option, a plus c greater than b. Second option, 4a plus 2b plus c greater than 0. Third option, a minus b minus c greater than 0. Fourth option, none. It's a beautiful question. Observe the data very, very carefully. Given that f of x is ax square plus bx plus c. Well, a greater than b square by 4c. Entire thing is involved here. A is greater than b square by 4c. Means 4ac greater than b square, or b square minus 4ac less than 0. As and when you notice that b square minus 4ac is less than 0, that equation ax square plus bx plus c is equal to 0 cannot have real roots at all. Cannot have real roots at all. Therefore, please recollect the graphs related to this situation. There are only two graphs possible. One graph is this, another graph is this. That is, the expression is always positive or the expression is always negative. How to recollect that? We are not given anything about A. If A is positive, this is the case. If A is negative, this is the case. Of course, one important information has been given. A plus b plus c is greater than 0. What does it mean? A into 1 square plus b into 1 plus c, that is f of 1 is positive. That is, we are able to have one positive value. If one value of f of x is positive, every value is positive. Every value is positive, because some f of x's are positive, some f of x's are negative. Does not arise, such type of cases does not arise there. The expression is always positive or expression is always negative. Only two cases arise here. And we are given to understand that f of 1 is positive. A plus b plus c, what is meant by a plus b plus c? F of 1 is positive. Therefore, f of 2 is positive, f of 3 is positive, f of minus 1 is positive, f of every real value is positive. Let us check the validity of all these. First one, is it true? If a plus c greater than b, what should happen? A minus b plus c greater than 0. A minus b plus c is greater than 0. That is, f of minus 1 is greater than 0. Correct. Isn't it? What is a plus c greater than b? See, every f of x is positive. That is, f of minus 1 is positive. What is f of minus 1? A minus b plus c, positive. Send this b to the side. What is going to happen? A plus c is greater than b. This is correct. Observe this. 4a plus 2b plus c. What is that? 4a plus 2b plus c is nothing but f of 2. As positive, this is correct. What is a minus b minus c? We are not able to have any f of x here. We are not able to decide here. These two are of course correct. Therefore, this is a question having multiple answers. This is correct. This is also correct. Well, it is very important, very crucial to observe the nature a plus b plus c greater than 0. As a plus b plus c greater than 0, immediately you must be in a position to see that it is just nothing but f of 1. One particular f of x is observed positive. According to the nature, every f of x must be positive. Therefore, a is given to be greater than 0. So, the graph looks like this. Means f of every real number is positive. You observe the options. The first one, a plus c greater than b, can be observed if you notice f of minus 1 greater than 0, which is true. So, this is correct. What about the case here? F of 2. Yes, f of 2 is also positive. Hence, this is also correct. But we are not able to trace any value as f of x to have a minus b minus c. This we cannot decide. So, you leave it. These two are the correct options here. A wonderful question based on those two graphs. That is, when b square minus 4 is less than 0, that is when the quadratic equation ax square plus bx plus c is equal to 0 does not possess real roots. The only thing that you can say is that expression is either always positive or always negative. It is always positive when a is greater than 0. It is always negative when a is less than 0. Yes, this is the way in which we understand the nature of f of x, that is ax square plus bx plus c, related to the roots of the equation. Let us now deal with the cases of solving some inequalities. How to solve x square minus 3x plus 2 greater than 0, x square minus 5x plus 6 greater than or equal to 0, x square minus 7x plus 12 less than 0, x square minus 9x plus 18 less than or equal to 0. These are very simple problems in which the quadratic expression lying in the left hand side can be factorized. Look here. This can be written as x minus 1 into x minus 2 greater than 0. Well, without drawing any graph or without recollecting any formula, we will be able to trace the region in which that inequality holds. This style, technique or method which you are going to learn is possible to be used when and only when the quadratic expression lying in the left hand side can be factorized, or that equation has two distinct real roots only. Like here, what are the roots here? 1 and 2. 1, 2. You just draw x-axis, plot the points 1 and 2. We want to have greater than 0. You put plus here. Why? Because if you take x here, x is greater than 2. So, this is positive, total is positive. Next one, here negative, here positive. That's all. We want to have the positive region. Therefore, x belongs to minus infinity to 1 union 2 to infinity. If you want to have x square minus 3x plus 2 less than 0, then this expression is just nothing but the same. The roots are 1 and 2, here positive, you put just alternative, plus, minus, plus. Of course, this technique can be used for only a quadratic expression in which the quadratic equation has two distinct real roots only. Let us of course extend the same technique for any cubic polynomial or fourth degree biquadratic polynomial having different roots later. Let us observe the same for a quadratic expression only. Well, so this must be greater than 0. What are the regions in which the expression is greater than 0? Either here or here. Here means x is behind 1 up to minus infinity. Therefore, x belongs to minus infinity to 1 or either here 2 to infinity. In the same question, if it has been asked x square minus 3x plus 2 less than 0, what is the region you have to pick up? Where does it lie? The negative values where are available? Between 1 and 2. That is, x belongs to the open interval 1 and 2. X belongs to open interval 1 and 2. To make it clear, let us consider one more such example. X square minus 5x plus 6 greater than 0. X square minus 5x plus 6 greater than or equal to 0. X square minus 5x plus 6 less than 0. X square minus 5x plus 6 less than or equal to 0. To avoid confusion, I have taken the same quadratic expression here in all these 4 problems. You can easily observe that the LHS can be factorized as x minus 2 into x minus 3. What are the roots here? 2 and 3. For all these expressions, it can be factorized as x minus 2 into x minus 3. Let me solve the first one. X minus 2 into x minus 3 greater than 0. What are the roots here? 2 and 3. Let us name those on x-axis. Well, let us start. Beyond 3, if you take x here, automatically greater than 3, minus 3, positive, positive. Total is positive. So, positive, negative, positive. Without any hesitation, without any doubt, we just put alternately plus and minus. Well, this is the first question. This is the second question. This is the third question. This is the fourth question. What is the answer for the first question? X squared minus 5x plus 6 is greater than 0. Where can you observe positive answer? Here or here? Here means, come on, minus infinity to 2 union 3 to infinity. Good. Second question answer. X square minus 5x plus 6 greater than or equal to 0. Equality is also expressed here. Therefore, in that case, the x can be less than 2 or equal to 2 is also possible. Therefore, minus infinity to 2 closed interval union there 3 to infinity. Well, let me see the case with third question. In the third question, what does he require? Expression must be less than 0. That is, x minus 2 and x minus 3 must be less than 0. Where can you have? Between 2 and 3. Between 2 and 3. Therefore, isn't it? X, when it lies between 2 and 3, then the expression is negative. Therefore, x belongs to open interval 2 to 3. And for the last question, automatically and evidently, x should belong to closed interval 2 to 3. In this way, without drawing any graph, justly looking at the roots of the equation, we are able to solve the given inequality like this. The given inequality like this. Now and then, he may ask you like this. 5x minus x square minus 6 less than 0. How can you solve like that? It is always suggestible. It is always suggestible to keep the coefficient of x square positive only to avoid minimum confusions. This can be traced again as x square minus 5x plus 6 greater than 0. Of course, by multiplying throughout with minus 1. This is the way in which we solve an inequality in which a quadratic polynomial which can be factorized is given. We shall now discuss with the case whenever the quadratic polynomial cannot be factorized at all. Cannot be factorized. Look here, x square plus x plus 1 is greater than 0. Solve. He is asking us. This cannot be factorized. Then and there itself you may suspect that. You first calculate the discriminant here. What is the discriminant here? B square minus 4ac is 1 minus 4 is minus 3, absolutely negative. So this expression does not possess real roots. Hence only two cases arise, either this case or this case. Can we be in a position to decide? Yes, of course. What is A here? 1. Positive. A is positive. Hence it is an upward opened parabola. This is always greater than 0. So solving this is a mere waste. By birth itself, lifelong it is positive. Therefore this is true for all x belongs to R. So if at all you are asked to solve this one, the answer is x belongs to R. For any real value it is true. Yes. In a similar fashion, if you are asked to solve this expression, what is the set of solutions? X square plus x plus 1, discriminant is less than 0. Discriminant is less than 0 means it does not possess real roots. So only two cases will arise. But of course A is positive. Hence compulsorily this must belong to this graph. So it is always positive. It can never be negative. What is the solution set here? 5. What is the solution set? 5. That is, you can find no real number x to satisfy this inequality. Now and then you may be deceived by giving such questions. You must be very careful and alert. It can be made only when observing the discriminant here and observing the coefficient of A here. Well, next one. So factorized expressions and those expressions are not to be factorized, both of them we have seen. Next one. X minus 1 into x minus 3 by x plus 1 into x minus 4 greater than 0. How to solve it? This must be greater than 0. You solve that inequality. Numerator is a quadratic expression. Denominator is also a quadratic expression. To find its range and finding the conditions of validity of that greater than 0 symbol is not very easy. Of course it is easy. We can apply the previous methodology here also. What are the roots of the expression here? 1, 3. Here minus 1, 4. You plot those points on x-axis in the increasing order. What is the least number? Minus 1. What is the next number? 1. What is the next one? 3. What is the next one? 4. Are there any repetitions here? That is what I mean is there any x minus 3 whole square, x minus 1 whole square, exponents? Are there any? No. Well, the largest number is 4. Positive, negative, positive, negative, positive. What does he want? Greater than 0. Come on, gather the regions in which the expression is positive. Case 1, case 2, case 3. So to solve it, let me name this as f of x. F of x is greater than 0 implies, come on, x belongs to first interval minus 1 and behind that up to what extent? Up to minus infinity. Therefore minus infinity to minus 1. The next positive region, come on, between 1 and 3. And the next positive region 4 to infinity. So this technique, rather this methodology, helps us a lot in solving expressions of this inequalities of this form. Again, if at all the problem is given to solve like this, if f of x is less than 0, then what are the regions to be picked up here? You look at the diagram, you observe what are the regions in which the expression happens to be negative. This is the first interval and this is the second interval. Very simple to solve this. We should have x in the interval -1 to 1 and other is 3 to 4. That's all. Not only like this, a cubic expression, a biquadratic expression, a polynomial expression involving greater than 0 or less than 0 can also be solved in a similar fashion using the technique. Well, let us see such cases now. X minus 1 into x plus 2 into x minus 3 into 2x minus 5 greater than 0. Solve it. It is not quadratic. Even then we will be able to solve it because it is factorized. It is supposed to have 4 different factors. What are the factors? Here you can see on the board. The roots of this expression, the roots of the equation when this is made equal to 0 are here 1, here minus 2. What are they? 1, minus 2, 3, 5 by 2. Isn't it? Arrange them on x-axis. What is the least one? Minus 2. Next great, next larger, 5 by 2, that is 2.5. The next 3. Good. Plus, minus, plus, minus, plus. Multiply. One more thing you can ask. Should we put plus always here? Yes, of course. If this is 1, 2, 3, 4 biquadratic expression, coefficient of x power 4 is positive. If this is positive and the answer is to be positive, here it must be positive. If I give like this, then it becomes negative. Isn't it? Forget it. Positive by negative, positive, negative, positive. What do you want? Positive. What are the regions? Here, here, here. Means x must belong to minus infinity to minus 2, union 1 to 5 by 2, union 3 to infinity. This is the answer. Suppose if that is greater than or equal to 0, then this interval becomes closed interval. Minus infinity to, let me call this f of x. If you are asked to have f of x greater than or equal to 0, then what is the answer? X belongs to minus infinity to minus 2, union 1 to 5 by 2, union 3 to infinity. Accordingly, f of x less than 0 and f of x less than or equal to 0 can also be solved. Can we say the answer for f of x less than 0? Why not? It is a union of two intervals. What are they? Open interval minus 2 to 1, union 5 by 2 to 3 is the solution for f of x less than 0. If you want to have f of x less than or equal to 0, then what is the answer? Closed interval minus 2 to 1, union closed interval 5 by 2 to 3. Accordingly, you will be in a position to solve such inequalities without hesitation and on the spot itself. Well, let us turn our head towards another corner of similar type of problems now. What type of speciality are you able to observe in this expression? X minus 2 occurs twice, that is why whole square is present. X minus 4 occurs thrice, that is why you are able to have x minus 4 whole cube. Then, is there any change in the procedure? Let us see. First of all, what are the roots? In the increasing order, let us trace the roots. -3, 1, 2, 4, 5. Come on. -3, 1, 2, 4, 5. As usual, beyond this largest one, positive. Let us first understand the style of putting these plus and minus symbols here. Observe this region. X is greater than 5. Greater than 5. Positive, 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 positive. That is why here it is positive. Well, between 4 and 5. Between 4 and 5 means this is negative. This is positive, 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 positive. Product is negative. Product is negative. Well, what do you say about here? Between 2 and 4. Between 2 and 4. This is positive. This is positive. This is positive. This is negative. This is negative. Negative into negative. This is positive. This is positive. This is positive. This is negative. This is negative. Total is positive. Between 2 and 4. Well, next 2 and 1. Between 1 and 2. 1 and 2 means this is positive. This is negative. This is, between 1 and 2, this is negative. This is positive. This is negative. This is negative. Altogether 1, 2, 3. It is negative. Next, between -3 and 1. -3 and 1. Where does it lie? Yes. -3 and 1. This part is negative. This part, -3 and 1. This is, as it is whole square, this is positive. This is -3 and 1, but this is +3. This is positive. This is negative. This is negative. How many negatives are here? 3. Again minus. Again minus. Here, as this is minus, this is plus. These are the reasons we have noted. We have noted. We now observe, without discussing such things, how can we be able to put these symbols? Positive, negative, x minus 4, exponent is 3. Odd number or even number? Odd number, so minus. Next, between 2 and 4. Between 2 and 4. Between 2 and 4, positive. Next here, x minus 2 whole square. It is plus minus. No, this is even number. The same sign is to be put here also. Minus, minus. Minus 3. Beyond that no more exponent is there. So the alternate symbol. Now greater than 0. Greater than 0 means what are the regions? Minus infinity to minus 3. Union 2 to 4, union 5 to infinity. Accordingly, you can solve that expression if it is supposed to be negative also. Very easy to pick the regions. What are the regions? -3 to 1, union, no, -3 to 2, union 4 to 5. That's all.